Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to the episode. I'm joined today by Jacob Nissen, Chief Sales Officer at Space Inventor. Space Inventor is a Danish satellite engineering company that specialises in nano and microsatellites and is a participant in the satsearch membership program. Today we're going to discuss extending CubeSat LEO platforms into GEO missions. Firstly, Jacob, welcome, and is there anything you'd like to add to that introduction?
No, I'm fine, thank you, and thank you for giving me this opportunity to join this conversation.
No problem, you're more than welcome. Okay, so let's dive into this topic. Now, Space Inventor's heritage dates back to kind of the early days of CubeSat platform development. And back then, CubeSats were known as being a little bit unreliable and had significantly high failure rates in comparison to other aspects of space technology, of course. How do you think the industry has evolved to deliver higher performances and higher reliability for CubeSat platforms today?
Well, I think different companies have taken different approaches to this. Some companies have done more qualifications of their products, but not really changed the way they're doing stuff. There is a tendency in this industry that once you have flight heritage, then you are maintaining your products as is. But for us at Space Inventor, we had the luxury to rethink how CubeSat should be built since we were established back in 2015. So we are looking into how we can obtain higher reliability and higher performance in our, you can say, satellite platform. And we have been inspired by how the traditional space industry is doing things, and then combine it with the more new space technologies like using COTS components. And then we also add the distributed software architecture to our systems. So once looking at the CubeSat, the first thing we did was get rid of the stack connector because this is really an unreliable component in the system where you use the stack connector to combine several components to a satellite bus. And this stack connector is, in our opinion, very unreliable, especially when you are assembling and disassembling your satellite bus, which happen quite often. So what we did was making all our subsystems and avionics systems into enclosures, which can then be used both for microsatellites and nanosatellites. And then we actually applied the PC-104 form factor so it actually also can fit into a CubeSat satellite. So having these kind of enclosures gives us quite a lot of advantages from a reliability and performance point of view. Firstly, of course, the shielding or the enclosure provides you with some shielding from radiations, but it also provides us with very good thermal properties where we can actually transfer the heat from our processing units or power processing units to the entire enclosure and then to the structure. That means that we can actually put more performance into our subsystems due to this. And then thirdly, we are actually also using high reliable connectors in a shielded enclosure, which provides you with a very low EMI properties for each subsystem, which makes it much more easy to integrate the final satellite without having any interoperability issues.
Interesting, yeah. So there's quite a lot has gone into the redesign and re-engineering of the systems, and of course we're just talking about the satellite itself there, the bus and aspects of the bus. Now, in the early days again of the CubeSat industry, there were a lot of payloads in use that were either experimental or due to certain performance limitations just could not be extended into commercial devices, services, maybe due to cost or just simply due to the output they were able to give when used in small sat platforms, CubeSat platforms, apologies. Now, as we see the nanosatellite industry maturing today, do you see there's more of a trend towards the sizes of satellite becoming bigger due to the fact that commercial applications are requiring payloads that need, higher mass, volume, power, etc., because of the performance levels that they're trying to achieve?
Yeah, it's a broad question in some way, because you will still see, for, you can say, student projects where you still are trying to learn how to make a satellite and an entire satellite mission program. There you still will see these very small CubeSats, in one or up to 3 U satellites. And then for commercial IoT satellite missions, you still want to maintain quite a low or small volume of your satellite. So we still see that these small IoT missions is still in the size of 3 to 6 U's, where you then apply larger deployable solar panels to get in the power enough for running it. But there is a big focus on still keeping the size of the satellite small to reduce the cost of the launch when you're doing quite a significant constellations of satellites. But I think for most satellites, and also the trend we're seeing, is that the satellites is becoming bigger, especially for, you can say, remote sensing applications, where you're either having RF signal intelligence or Earth observations. Here we see that you want, especially for Earth observation satellites, you want resolutions down to 0.5 meters in 500 kilometers altitude. And when you need this very low resolutions, then naturally the satellite becomes bigger, because the aperture of the camera needs to be bigger. So this is also the reason why Space Inventor has been focusing on building not only CubeSats but also microsatellite platforms. So we have a focus on building platforms up to more than 100 kilograms with high performance racks and wheels, so we can do very accurate pointing, together with the star tracker that we provide together with Therma, another Danish company that has a very long track record in star trackers. So what you'll see is we are actually also, for Earth observation satellites, we are introducing also a new line of communication solutions, both within S and X band radios. The first one will be handling up to data rates up to 20 megabit per second, but our next version of our X-band product will go up to more than 300 megabit per second. Also, you'll see satellites becoming bigger for SAR radars, where we're also making a platform where the power consumption is much larger. So here is our next invention that's coming in within the next year, is a power solution that provides you with kilowatt in the kilowatt range of the power that we can generate on our bus.
Interesting. So it's very much driven by the different applications available, and as you said, there are certain teams in research and student teams that still need these less high performance systems in a smaller form factor. But it's interesting that there's an overall trend in you've seen in the industry, and another obviously another area that you're looking at taking your experience is from the development of LEO based small spacecraft towards GEO missions. Now, this seems on the face of it like a big undertaking. What challenges are you seeing in delivering a small spacecraft platform for a GEO mission, and how are you overcoming such issues?
Yeah, I would say that going from GEO to GEO is quite a significant step in the complexity of the mission. You have a more harsh environment from a radiation point of view, but also that we actually need to maneuver the spacecraft from different orbital slots within GEO. So, but going first to the environment, we actually have done quite a lot for handling the radiation environment. one of the things we've done during this project, but actually also as before we started this project, was to have a kind of a simulation tool where we can actually take our 3D CAD drawing of the actual system, and then we can calculate what kind of radiation exposure each component in the system will have, and then we can actually apply spot shielding in the spacecraft where it will become necessary to do so. Another thing is that we in the spacecraft, everything is built also with complete redundant systems, and for our propulsion systems, which is a very critical component in the spacecraft, we actually have a triple redundant system. So we know that if something fails, we always have the capacity to move ourselves to the geo graveyard. And also from a software point of view, we've done quite a lot to measure the performance of all our systems. So we know that they are all operating and there's not been changes to the memory. And then we have built the software in a way where we can actually recover very fast. So we can actually recover and continue our mission within milliseconds in our software platform. For maneuvering, we also incorporated what you call ranging. So for ranging, you're actually using ranging for establishing your actually position in geo. Some people have been trying to use GPS, but normally GPS doesn't work in geo. So you need another way of finding your exact propulsion location. And then we are actually using up to four propulsion systems to perform station keeping and also do wheel unloading. In traditional in LEO, you are using magnetorquers to do the wheel unloading, but in GEO, the magnetic field from the Earth is so weak that you can't apply magnetorquers for this. So for wheel unloading, you actually need to apply propulsion systems. And then we're also having the propulsion system for or an electrical propulsion system to do the orbital maneuvering, going from one slot to another. And actually also we are using this for the initial orbital insertion, because we are, even though people say we are being injected directly into GEO, we are actually being dropped off 1,000 kilometers below the GEO orbit. So we still need to move towards our original orbital slot by using our propulsion system. So what we've done as well is to make sure that our entire AOCS systems is built together so we can actually simulate how a thrust will impact the rest of our AOCS system, so we can establish how much impact it will have on our wheels when we're doing a thrust. And one of the things we've learned as well is that we need to make sure that it's is flexible enough. Then we are having the capability of doing thrust vectoring, so we can compensate for different changes of the mass of the spacecraft. And for now, you can say the project we are having now, we actually passed the critical design review, and we are actually now start building the spacecraft. So we are, you can say, through most of the biggest design challenges, and we are now quite confident that we'll have a successful mission. So we are looking forward to our mission launch, which will happen early next year.
Fantastic. Well, obviously, best of luck with it. Sure, it'll all go well. It's surprising how much is involved in expanding the capability from LEO to GEO. I mean, yeah, aspects of it that you wouldn't think about. And given those sort of limitation or potential limitations, if notwithstanding your engineering approach, when we're talking about the requirements for the propulsion, both for orbital transfer and pointing, the lack of the inability to directly locate the increased radiation shielding required, ultimately, what kinds of payloads and services do you see that could really emerge as very strong options for geo-based small spacecraft, small satellites? Do you see more missions in this direction? Do you see there being a real opportunity here?
I think this will be a niche market, but there will definitely be more missions coming in. The payload will primarily be with communication missions, where you have communication transponders on the spacecraft. Either for, you can say, very local area networks where you are having a kind of a restricted communication system, or I know also people are looking into making an IoT solutions from a geostationary satellite instead, because it has the benefit that, once you've deployed one satellite in a specific region, then you can service, initially just with one satellite, you can service an entire area. Whereas if you have a LEO satellite, then you need a larger constellation to provide the same 100% coverage in time. So it will be definitely, IoT can be an interesting thing. Otherwise, we are also working with another company on what they call life extension missions, where you are actually building a smaller spacecraft that will then dock onto another existing geostationary satellite and then assist with the station keeping on the original satellite, where then you can maintain or extend the lifetime of the satellite, because you can save some fuel on the existing satellite so it can operate for a longer time before it has to go to the graveyard. So there are different applications, but they are mainly within communication missions or in life extension missions.
But it's sort of a different way of looking at the business aspect of it, because you've got a higher upfront investment required. So you need a mission application that's wide enough, large enough, I guess, to make back that investment.
That's true. You have a higher, upfront investment, but you also up and running, just with one satellite commission, then you can actually do the service by full, and not wait that you are, deploying a full constellations of hundreds of satellites.
Interesting. So, what about from the mission design aspect of it? Is it how have you found it extending the practices around quality control and reliability that have been established for LEO missions and services and equipment? And are there challenges in the supply chain, for example, because many of the components that are built for LEO CubeSats can't be at least easily used in GEO, as the environment is so different, as you've
Yeah.
discussed.
So actually, that was one of the key points that actually enabled Space Inventor to take on this mission to GEO, because our systems originally was built with much higher quality standard from the beginning. So we have actually been able to reuse most of the systems we've built. Of course, we have done some smaller adjustments to our hardware and software, but mainly due to our, you can say, original design with high performance and quality in mind, we could actually reuse those. Uh, and then also we're in this, you can say, good situation that we actually had a physicist in our team that has experience, and his domain is radiation impacts on electronic circuit boards. So we actually had the knowledge in house to actually to guide, you can say, the electronic development team of how they should build the circuit boards, and what is good practice. So we actually put that into our initial designs as well. Of course, we have done some new, more critical selections of. We are still using COTS components, but we are having a little bit more critical selection process towards what are the impacts on radiations. And then, as I mentioned previously in our conversation, is that we've made a complete redundant system. So if something will fail, and it probably will fail, then we will have other subsystems that will take over. So we built a little bit more resilient satellite platform instead of making it just robust.
Oh, fascinating! That's really interesting. Really interesting to learn about the approach there. So,
Yeah.
and it sounds like there was certain advantages that you had, which maybe put you ahead of other companies or other teams. So that's great to, I guess, have an opportunity to use them. So that's great. Now, aside from, I guess just to finish up, aside from you've got the mission coming next year, like you said, and you mentioned partnership with an organisation that you're going to be working on the station keeping, etc., for an existing satellite. What do you think are the most exciting changes that you're seeing in the industry and on the topics that we've talked about in the next 5 years? What's most exciting you guys there at Space Inventor?
Well, I think what we were hoping to see as well is that we're actually now going to see that the new space industry as such are going to make, and deliver profitable services to customers around the world from space activities. And also, we are not hoping, but I think we are seeing a trend that, people will be selecting the satellite platforms where, quality, lifetime, and the performance is more key parameters in the selection than not just having, the lowest price for doing a demonstration of satellites. So I think we see that we have put ourselves into the sweet spot for the next 5 years, that with, early on high focus on quality and making sure that we actually have systems that performs both for microsatellites and CubeSats. So I think we put ourselves in a nice place where, where people, when they want to do more commercial missions, then that they will choose our platform for the coming missions. So I think for us, we see quite a promising future from our platforms, especially also now that we also had some flight heritage of our existing platform.
Well, fantastic, and I hope that things play out like you're hoping for. So, and as I've said, best of luck with the upcoming mission next year. And it's really interesting to find out more about all the work at Space Inventor and about, in particular, the topic that we discussed today, expanding the capabilities and the possibilities that LEO spacecraft and applications can bring into the GEO domain. So I think you will have helped our listeners learn a lot about that topic. So thank you very much for spending time with us today, Jacob.
You're more than welcome.
That's great, thank you. And to all our listeners out there, remember you can find out more about Space Inventor on the SatSearch platform. You can find out about the products that the company offers, the sort of services that are available, and request more information about technical details, documents, introductions to the business, quotes, whatever you need for your procurement and trade studies and your mission development yourself. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.